Hey everyone, welcome back to the Deep Dive,
Yeah, welcome back.
the show where we cut through the clutter and really get to the heart of things.
Exactly.
And you're here because you like to understand complex topics, but you don't have all day to wade through tons of information.
Right.
So today we're diving into the fascinating world of exponents and powers. At first glance, it might seem like just a bunch of tiny numbers up high.
Yeah, these little superscripts.
But these little guys, these exponents, are actually the key to understanding incredibly large numbers.
Absolutely.
Like, the number of stars in a galaxy, or incredibly small numbers.
Like the size of an atom?
Exactly.
Hi.
And we've got some great resources here that break down exponents in all their glory.
Yeah, we do.
From the basics, the positive exponents to those sometimes tricky negative exponents.
Right.
And then how those tie into scientific notation.
Yeah.
So in this deep dive, we're going to demystify all of this exponent stuff. And by the end, you'll be able to wield these powerful mathematical tools.
You got it.
Like a pro.
Like a pro.
All right, so let's start with the basics.
Yeah.
What exactly do we mean when we see something like 10 to the power of 24?
Okay, so 10 to the power of 24, also written as 10 with that little 24 up top.
Yeah, that little 24.
It basically means we're multiplying 10 by itself 24 times.
Oh.
Yeah. And, as our resources point out, that's actually how we can express the mass of the Earth, which is a pretty big number, right?
Yeah, that's pretty massive.
Around 5.97, followed by 24 zeros kilograms.
24 zeros.
Yeah, think about writing all those zeros.
I don't want to do that.
Much easier to just use 5.97 times 10 to the power of 24.
Oh, for sure. Much more compact.
It's much more compact.
So it's really about efficiency.
Right.
It's like a mathematical shorthand for these huge numbers.
Right. And the same principle applies to other bases. Like the material also mentions 2 raised to the power of mom.
Yeah.
It's just 2 multiplied by itself times. It's all about simplifying repeated multiplication.
Okay, so far so good.
Yeah.
But then the material throws us a bit of a curveball.
Yeah, a little bit.
What about negative exponents?
Uh-huh.
Like, what on earth does 2 to the power of -2 even mean?
Right. This is where things get really interesting.
Okay.
And our sources do a great job of explaining this using patterns.
Oh.
Like, let's take powers of 10 as an example.
Right.
We know a 10 squared is 100, right?
Right, 10 times 10.
10 to the power of 1 is just 10.
Uh-huh.
Now, notice what's happening here. Each time the exponent decreases by 1, the value becomes 1/10 of what it was before.
That's interesting.
Yeah, so if we follow this pattern, 10 to the power of 0 would be...
Well, 1/10 of 10, so 1.
Exactly 1.
Oh, wow.
And then if we keep going,
Yeah.
10 to the power of -1 becomes 1/10 of 1, which is 1/10.
Oh, I see.
And then 10 to the power of -2 becomes 1/10 of 1/10.
Which is 1 over 100.
Exactly 1 over 100.
So that negative exponent, it's not about making the number negative.
Right.
It's about dividing instead of multiplying.
Absolutely.
Well, that's pretty neat.
It's like the flip side of a positive exponent.
Yeah, yeah.
And that brings us to the general rule, which the source lays out really well.
Right.
For any non-zero number a,
Yay.
and any positive integer n to the power of -m is equal to 1 divided by a to the power of m.
So it's like a reciprocal?
Exactly. It's the multiplicative inverse.
Ah.
And the source gives some great examples, like 2 to the power of -4.
Right.
It's just the inverse of 2 to the power of 4.
Huh?
And you can think of 10 to the power of -5 the same way.
Yeah.
It's the inverse of 10 to the power of 5.
And so on and so forth.
And so on.
You could even have 10 to the power of -100,
Oh, yeah.
which is just mind-bogglingly small.
Incredibly tiny.
But it still makes sense in the context of these rules.
Right.
And this isn't just limited to base 10, right?
No, not at all.
The material shows how it works with other bases, too.
Yeah, like let's look at base 3.
Okay.
So 3 cubed is 27.
Right. 3 times 3 times 3.
3 squared is 9.
Uh-huh.
3 to the power of 1 is just 3.
Yep.
And 3 to the power of 0 is 1.
Following the path.
Following the pattern.
Okay.
And then if we go into the negatives, 3 to the power of -1
is 1/3.
is 1/3.
3 to the -2 is 1 over 9.
That's right.
And 3 to the -3 is 1 over 27.
Exactly.
So that initial question about 2 to the power of -2,
Yeah.
we can now answer that pretty easily, right?
Oh, yeah. It's just 1 divided by 2 squared, which is 1/4.
So the principle's the same no matter what the base is.
Absolutely.
That's cool.
It's a universal concept in math.
It's like the exponent is like a little signpost
Yeah, I like that.
telling you which direction to go.
Mm-hmm.
Positive means multiply, negative means divide.
I like that analogy.
And the base tells you what number to use.
Exactly.
And this idea even extends to how we write numbers in expanded form.
Right.
Like with decimals.
Yeah.
So we're used to seeing a number like 1,425 expressed as.
1 times 10 cubed plus 4 times 10 squared plus 2 times 10 to the power of 1 plus 5 times 10 to the power of 0.
Right. Yeah.
But what about the digits after the decimal point?
Yeah. What about those?
Well, we can use negative exponents to represent those too.
Oh, really?
Yeah, so for example, 1 times 25.36 can be written as 1 times 10 cubed plus 4 times 10 squared plus 2 times 10 to the power of 1 plus 5 times 10 to the power of 0.
Okay, I'm following so far.
Plus 3 times 10 to the power of negative 1 plus 6 times 10 to the power of negative 2.
So that 3 in the tenths place?
Yeah.
It's actually 3 times 1/10.
Right.
And that 6 in the hundredths place
Is 6 times 1 over 100.
Wow, so our whole decimal system is built on powers of 10 going both up and down.
It's all connected.
Oh, that's amazing.
It's a beautiful system.
It really clarifies what those decimal places actually mean.
Right, it's not just some random placement.
Yeah.
It's all based on powers of 10.
And the source even encourages us to try this out with other numbers.
Yeah, it has a couple of examples like 1025.63 and 1456.249.
Right, to see how all the digits fit into this pattern.
Exactly.
It's a great way to really solidify the concept.
It's a fun exercise.
Okay, so we've got a good handle on what exponents are,
Yeah.
both positive and negative.
Right.
But how do these things actually work together when we do calculations?
Right, well, that's where the laws of exponents come in.
Laws of exponents.
Yeah, and our sources do a great job of breaking those down.
Okay, so what are some of the key laws we need to know?
Well, one of the most fundamental ones is when you multiply powers with the same base, you simply add the exponents.
Like a to the power of m times a to the power of n equals a to the power of m plus n.
Exactly. And what's really cool is that this rule holds true even when I'm and n are negative.
So the same rule we use for positive exponents works for negative ones too.
Exactly. It's very consistent.
That's great.
Yeah, it makes things a lot simpler.
And the material gives us some specific examples, right?
Yeah, to illustrate this, like 2 to the power of negative 3 times 2 to the power of negative 2.
Okay.
If we add the exponents negative 3 plus negative 2, we get negative 5.
Uh-huh.
So the answer is 2 to the power of negative 5.
Oh, that's straightforward.
Very straightforward.
Another example was negative 3 to the power of negative 4 times negative 3 to the power of negative 3.
Right. So adding negative 4 and negative 3 gives us negative 7.
So the result is negative 3 to the power of negative 7.
Exactly. And this works even when you have a mix of positive and negative exponents.
Like 5 to the negative 2 times 5 to the power of 4.
Right.
So negative 2 plus 4 is 2.
So it simplifies to 5 squared.
Easy peasy.
And the source gives one more example with negative 5 to the power of negative 4 times negative 5 squared.
Negative 4 plus 2 is negative 2.
So we end up with negative 5 to the power of negative 2.
So no matter what combination of positive or negative exponents we've got,
yeah,
this rule stays consistent.
absolutely. It's a fundamental principle.
It's beautiful.
It is.
Okay, so that's one key law of exponents. What other ones do we need to keep in mind?
Well, there are a few others that are really important.
Okay, maybe with them.
When you divide powers with the same base,
Okay.
like a to the power of m divided by a to the power of n,
Uh-huh.
you subtract the exponents, so you get a to the power of m minus n.
Okay.
Then there's raising a power to another power, like a to the power of m all raised to the power of n.
Yeah,
In that case, you multiply the exponents to get a to the power of m times n.
got it.
And when you multiply powers with different bases but the same exponent,
Okay.
a to the power of m times b to the power of n, you can combine the bases.
So a to the power of m.
Exactly, and the same logic applies to division.
So a over b, all to the power of m equals a to the power of m over b to the power of m.
Precisely.
And lastly, we can't forget that any non-zero number raised to the power of 0
Is always 1.
always 1.
Yeah, that's a fundamental one.
It's like a magic trick.
It is kind of magical.
But as we saw earlier with the powers of 10, it actually makes sense.
It fits right into the pattern.
Yeah, it all comes together.
Right.
Okay, so these are the rules.
Yeah.
But how do we actually use them in
The
practice?
source gives us a bunch of great examples.
Okay, let's dive into those.
Okay, so first let's look at how to find the value of 2 to the power of negative 3.
Right.
We already know that this is 1 divided by 2 cubed, right?
Right, which is 1 over 8.
Exactly 1/8. Now let's try something a little trickier.
Okay, bring it up.
What about 1/2 to the power of negative 3? Now here's a handy rule. When you have a fraction raised to a negative exponent, you can flip the fraction and change the exponent to positive.
Oh, that's a good trick.
So 1/2 to the power of negative 3 becomes 2 over 1 to the power of 3.
Which is just 2 cubed or 8.
Exact.
So that negative exponent essentially flipped the fraction.
It's a neat shortcut.
Very neat.
The source also shows us how to simplify more complex expressions, like -4 to the power of 5 times -4 to the power of -10.
Okay, so we can use that first law we talked about.
Right, adding the exponents,
So we get -4 to the power of 5 plus -10.
which is -4 to the power of -5.
And that can also be written as 1 divided by -4 to the power of 5.
Exactly.
Like, how about a division example?
Okay, let's try 2 to the power of 5 divided by 2 to the power of -6.
So we subtract the exponents, right?
That's right,
So it's 2 to the power of 5 minus -6,
which simplifies to 2 to the power of 11.
because 5 minus -6 is the same as 5 plus 6.
Exactly. It's important to remember those sign rules.
Absolutely.
Now, the source gets even more interesting with an example where we need to express 4 to the power of -3 as a power with base 2.
So we need to change the base.
Right. And the key here is recognizing that 4 is the same as 2 squared.
Oh, right.
So we can substitute that in and get 2 squared to the power of -3.
And then we use that rule about multiplying exponents when raising a power to another power.
Exactly. So 2 times -3 gives us -6.
So the answer is 2 to the power of -6.
That's it. We've successfully changed the base.
Yeah.
And then there's a really cool example that combines several of the laws.
Wait on me.
It's 2 to the power of 5 divided by 2 to the power of 8, all raised to the power of 5, and then multiplied by 2 to the power of -5.
Whoa, that's a mouthful.
Yeah, it looks complicated.
But we can break it down step by step.
Absolutely, just follow the order of operations.
First, we simplify inside the parentheses.
Right, so 2 to the power of 5 divided by 2 to the power of 8, that's 2 to the power of 5 minus 8, which is 2 to the power of -3.
Got it. Then we raise that to the power of 5.
So we get 2 to the power of -3 times 5, which is 2 to the power of -15.
And finally, we multiply by 2 to the power of -5.
So we add those exponents and get 2 to the power of -20.
Wow. It's like solving a puzzle.
It is a bit like a puzzle.
But by applying the rules systematically, we get to the solution.
That's the key.
The source also gives an example with multiple bases, but the same exponent.
Right. -4 to the power of -3 times 5 to the power of -3 times -5 to the power of -3.
So here we could use that rule about combining bases when the exponent is the same.
Exactly.
So we get -4 times 5 times -5, all raised to the power of -3.
Which simplifies to 100 to the power of -3.
Because -4 times 5 times -5 is 100.
Right.
That's a neat trick.
It is.
And then there's an example where we have to use a bit of algebra.
Right. Finding the value of m in the equation -3 to the power of m plus 1 times -3 to the power of 5 equals -3 to the power of 7.
Okay, so first we can simplify the left side of the equation.
Yeah, we have the same base, so we can add the exponents.
So we get -3 to the power of m plus 6.
Because m plus 1 plus 5 is m plus 6.
And that equals -3 to the power of 7.
Right, so for the two sides to be equal, the exponents must be equal.
Meaning m plus 6 must equal 7.
And if we solve for m, we get m equals 1.
All right, and before we move on to standard form,
Yeah.
the material has one last example about negative exponents with fractions.
Right, it's 2 over 3 to the power of -2.
So we can flip the fraction and change the exponent to positive,
Exactly, so we get 3 over 2 squared.
which is 9 over 4.
That's right.
Okay, so we've thoroughly covered the laws of exponents,
We have.
both for positive and negative exponents.
Huh?
Now let's see how we can use these concepts to express very small numbers.
Right, in standard form or scientific notation?
So we've seen how this works for really big numbers.
Yeah, like the mass of the Earth.
But what about the tiny ones?
Well, it's the same principle, just with negative exponents.
Oh, okay.
The source gives a good example, 0.00000007 meters.
Okay.
That's the same as 7 divided by 1,000,000.
Which is 7 divided by 10 to the power of 6.
Exactly. And using our knowledge of negative exponents, we can rewrite that as 7 times 10 to the power of -6 meters.
Much more compact
Much more manageable.
and easier to understand.
Absolutely.
Another example they give is the thickness of a piece of paper,
Right, 0.0016 centimeters,
which we can rewrite as 1.6 divided by 1,000.
which is 1.6 divided by 10 to the power of 3.
So in standard form, it's 1.6 times 10 to the power of -3 centimeters.
That's it.
So that negative exponent is telling us how many places we've moved the decimal point to the left.
Exactly.
And the source even encourages us to try this out with some other numbers.
Yeah, like 0.00000000000000021.
Just to get the hang of converting between decimal form and standard form.
Right. Practice makes perfect.
And it also reminds us of some real-world examples where these tiny numbers come up.
Like the diameter of a red blood cell or the thickness of human hair.
Things we can't even see with the naked eye.
It's amazing how much smaller the universe gets
It is.
when you start using scientific notation.
So now we have this powerful tool to express both the massively large and the incredibly small. But what's really cool is how we can use standard form to compare these vastly different scales.
Right. The source gives a perfect example.
The sun and the Earth.
The sun's diameter is 1.4 times 10 to the power of 9 meters.
And the Earth's diameter is 1.2756 times 10 to the power of 7 meters.
The Earth's diameter is 1.2756 times 10 to the power of 7 meters. Just by looking at the exponents 9 and 7, we can see that the sun is much bigger.
And if we want to be more precise, we can divide the two numbers.
Yeah, so 1.4 times 10 to the power of 9 divided by 1.2756 times 10 to the power of 7.
That simplifies to about 1.1 times 10 to the power of 2.
Meaning the sun is roughly 110 times wider than the Earth.
It's incredible how easily we can compare these sizes using standard form.
It's a very powerful tool.
And we can do the same thing with tiny objects.
Yeah, like comparing a red blood cell, which is 7 times 10 to the power of -6 meters.
To a plant cell, which is 1.275 times 10 to the power of -5 meters.
Here the exponents are -6 and -5.
So we know they're both very small.
Right.
But the plant cell is slightly bigger because -5 is greater than -6.
Exactly. And the coefficient 1.275 is also bigger than 7 when we adjust for the difference in the powers of 10.
So standard form makes it easy to see these subtle differences in size.
It's a great tool for comparison.
The material also briefly mentions adding and subtracting numbers in standard form.
Right. And the key point there is that it's easiest to do these operations
when the numbers have the same power of 10.
Yeah, like if you wanted to calculate the total mass of the Earth and the Moon.
You'd need to make sure they both have the same exponent.
Exactly. And then you could just add the coefficients.
So it goes for subtraction.
Right. Like if you were calculating the distance between the Moon and the Sun during a solar eclipse.
You need to subtract the Earth-Moon distance from the Sun-Earth distance.
And making sure those exponents are aligned is crucial.
Absolutely. Otherwise, you could get a totally wrong answer.
Right.
Okay. And finally, the source gives us some examples of converting numbers back and forth
between standard form and usual form.
So we can see how these two representations relate to each other.
Right. Like let's say we have 0.000035.
To convert that to standard form, we move the decimal point 5 places to the right.
And get 3.5 times 10 to the power of -5.
And if we want to convert 4.05 times 10 to the power of 6 back to usual form,
we move the decimal point 6 places to the right.
To get 4,050,000.
And for a number like 7.54 times 10 to the power of -4.
We move the decimal point 4 places to the left.
To get 0.000754.
So the exponent tells us how many places to move the decimal point.
And in which direction?
Positive exponent moved to the right, negative exponent moved to the left.
Exactly.
The source wraps up by referencing exercise 10.2 and some of those real-world examples.
Yeah, just to emphasize how important standard form is.
Especially in science and technology.
Absolutely.
So the key takeaway here
is
that exponents are incredibly powerful tools.
They really are.
They allow us to work with numbers that are either incredibly large
or incredibly small.
And they make it much easier to compare and calculate with these extreme values.
Right, and it's not just about abstract math.
No.
These concepts are used in all sorts of fields.
From astronomy
to microbiology
to computer science
and finance.
So understanding exponents is really essential for understanding the world around us.
Absolutely.
And it leads to a really interesting thought. Think about all the advancements in technology that have been made possible by our ability to work with very small numbers.
Right, like nanotechnology. We're talking about measurements on the scale of nanometers.
Which is 10 to the power of -9 meters.
Without exponents and scientific notation.
It would be almost impossible to work with these tiny values.
Right.
And the same goes for astronomy.
We're dealing with distances measured in light years.
And masses of stars and galaxies that are just mind-bogglingly huge.
Exponents are essential for making sense of it all.
It's a reminder that math isn't just some abstract subject.
Yeah.
It's a tool that allows us to explore and understand the universe.
It's the language of the universe.
Exactly.
So as you go about your day,
Yeah.
pay attention to the numbers you encounter.
Especially the really big ones and the really small ones.
See if you can express them using exponents and scientific notation.
It's a fun little exercise.
It is.
That can really deepen your appreciation for the power of math.
Absolutely.
All right. That's it for today's deep dive.
Thanks for joining us.
We hope you learned something new.
And had some fun along the way.
Until next time, keep diving.
Keep exploring.